Thank you, Chairman. Good evening. I'm Yusuke Seko from Tokyo Gas Fundamental Technology Research Institute. Today's my presentation title is the effect of residual stress and crack configuration on Weibull stress for weld straight with crack. I start with the background. So for the brittle fracture assessment, you know the conventional method sometimes provides excessively conservative safety assessment results. This figure, the 3-point urban specimens have a high stress field region compared to the wide-braided specimen, like the axial structure component. So the fracture toughness value obtained by the 3-point bend specimen gives a low fracture toughness results. To solve this problem, recently as a local Weibull stress was used as a fracture driving force. The Weibull stress is shown in this equation. To calculate this equation, it requires a very complex perimeter analysis. So the ISO 27306 was specified in 2009 by the Professor Minami. This standard gives equivalent CPU radio data. If using this equivalent CPU data, you can calculate the critical CPOD for the actual component from the critical CPOD for the 3-point bend specimen. This is very useful for the engineers. But however, the ISO standard is now only applicable to assessment of the both interface method. So the others, we now focus on the applicability of Weibull stress criterion to brittle fracture or embedded crack in welded joint. I explain briefly. This is we prepared this wide-braided specimen. We succeeded to make the embedded crack generated by the cold cracking naturally. Then this test specimen was tensioned along the vertical direction to the embedded crack surface. Then brittle fracture was occurred from the embedded crack. This bottom figure shows the fracture surface of the embedded crack. Then we conducted the finite element analysis to predict the brittle fracture limit for the wide-braided tension test. Then we confirm that we can predict the tension load as a brittle fracture. Tension load after brittle fracture is calculated by the CPOD obtained by the 3-point bend analysis. P is a Weibull stress. But these measures require very complex measures. It is not easy. So the establishment of assessment methods such as ISO 27306 to price a plastic constraint for the welded joint is expected. But there is a many influence factor for brittle fracture limit of embedded flowing joints. Now we focused on the above two factors. One is the welding resistance, and the second is the crack depth. So my objective of this study is to clarify the effect of crack depth and welding resistance on the brittle fracture limit of embedded flow based on Weibull stress criterion using a finite element analysis. First of all, I will explain the effect of crack depth. Here's a finite element analytical model. We use flat plate model with 200 mm wide and 200 mm length. And then this flat plate has embedded cracks like this. This embedded cracks have the 3 parameters. One is the crack depth H, and the second is the crack height A, and third is the crack length C. And then the minimum mesh size on the crack chip was set to the 0.05 mm times 0.05 mm times 0.2 mm, and the thickness of this flat plate was thickness of this flat plate was 25 mm. And then in modeling, by considering the symmetry, the quarter model was used. And then Abacus version 6.13 was used for the FEM code. And inputted material properties shown in this table. This is 70, 180 micrometer plus 2. And then we conducted six cases analysis. The crack size was variated. Crack height 2A equals 6 mm and 9 mm, and the crack length is equal 40 mm. And the crack depth is, in case of crack height 6 mm, crack height depth is 2 mm, 6 mm, 95 mm. And in the case of crack height 2A equals 9 mm, crack depth is 2 mm, 6 mm, 8 mm. And then output parameter was shown here. Weibull stress around the crack tip was calculated, and Weibull stress shape parameter M equals set to 20. And then CDOD at the shallowest point and the deepest point of the embedded crack was calculated. In this study, the shallowest point is called to the top, and the deepest crack tip point is called bottom. And the CDOD was calculated by the condition method. And the strain and the crack opening stress was calculated. And here is the result. CDOD as crack breaking force. The left figure shows crack height is 6 mm, and the right figure shows the crack height is 9 mm. And so this figure shows the relationship between overall strain and the CDOD. And you can see the CDOD at the top of the shallow crack model was relatively higher than the other cases. And then the black line shows the middle embedded crack model for the thickness. The other cases is slightly larger than the middle embedded crack model. So the CDOD at top and beauty increased with decreasing crack depth at the same overall strain level. And this tendency was same as the crack height is to be 9 mm cases. And then here is opening stress distribution. Here is a crack shape. This graph shows the relationship between the distance from crack shape and opening stress. You can see the opening stress at the top of the shallow model was smaller than the other cases. This means the plastic constraint of the top for the shallow crack model was locally lower than the other cases. On the other hand, the opening stress at the top for the shallow crack model was larger than the other cases. But not it's has the same tendency. And then this is the same as previous figures. This is a visualized figures. You can see the shallowest crack tip point has no high plastic stress fusion. You can see it was relieved because this crack tip point was near the chicken surface. However, here is the plastic constraint calculated result. The graph shows the relationship between CDOD and the Weibull stress. At the same CDOD level, you can see the shallowest Weibull stress of shallow crack model was higher than the other cases. Then the other cases were almost the same. Then, here's a breakdown about the breakdown fracture limit. The graph shows the relationship between overall strain and Weibull stress. And you can see the model with crack depth equals 6 mm, and the middle embedded crack model was almost the same in all overall strain region. But the shallow crack model with h equal 2 mm was larger than the other cases, over the 0.2% strain. And this is the same as the 9 mm cases. This means based on the Weibull stress criterion, brutal pressure limit of embedded crack decreases with decrease in crack depth in your region. The second is I explained the effect of welding residual stress. Here is an analytical condition. It's, the model shape and the model properties and were same as the previous analysis. And then the welding registers of cable welded joint made by 780 Pascal steel was introduced to analytical model. Left figure shows comparison between experimented obtained welding residual distribution and the simulated welding residual distribution. You can see the open mark means the experiment data, and the black solid mark means simulated results. You can see that these are good arguments. And this figure shows a storage fusion after introduced this welding residual stress to analytical model. Here is the CTOD as crack driving force. You can see the welding residual stress didn't affect the CTOD as crack driving force in case of shallow crack model. Shallow means red lines, and there is no big difference. And in the case of the middle embedded crack model, there's a slightly difference, but I think that is no big difference. The tendency was same as the 90 meter height. And here is a plastic constraint. You can see the line is marked in case with residual stress. You can see both the shallow crack model and the deep crack model with residual stress was higher than the other cases without residual stress model, and especially for the in small deformation region. After big deformation region, which is getting to be close to each other. This tendency is same as the 90 height. And then here is the breakthrough fracture limit. About the breakthrough fracture limit. You can see both the shallow crack model for the red line and the deep crack model black line is there is a difference between the without residual stress model and with residual stress model. So the welding residual stress decrease the breakthrough fracture limit of embedded crack before overall strain reaches yield stress, because after yielding yield strain, this is getting to be close to each other. This is a conclusion. Thank you for your kind attention.